All right, ladies and gentlemen, this is just a review video for Unit 7 on simple harmonic motion. And similar to previous, or I'm sorry, the last review video I did, I'm going to focus more on the concepts as opposed to the actual math, doing out the problems. Many of you have had more issues with doing out with the concepts, with the multiple choice questions, as compared to the free response. So based on that, I think the time would be best used trying to tie down some of those loose concepts. So to start off with, I just want to kind of go through a lot of the equations and talk about the concepts that go into them. Not necessarily how to do the problems with those, but the concepts. And the first two are our period equations. One of the big things on the test is going to be knowing what affects each one of those. If you change the mass of the object that is on either the spring or the string of the pendulum, which of those two things does that affect? Well, it affects the period of the spring because mass is in that equation, but mass is nowhere here in the period of the pendulum. Same thing with going to a different planet. If you go to a different planet, the pendulum changes, the G is in there, but the spring experiences no change in the period. Just a reminder, if you double one of those variables, that does not have the exact same effect on the period. Remember, it's a square root. So in order to double the period of a spring, you'd have to quadruple the mass. Same with the length for a pendulum. Down here below, we've got F equals Kx. That is Hooke's law. Working with springs, that is helpful, but it's also equal to ma. So if you're looking for a particular acceleration and you know Kx and m, you can actually solve for that. This is not one of the equations that's given to you on the green sheet. Everything else is. But this is not. This is a particular situation where the Kx equals ma, as long as the spring force is really your only force that is acting, and you make sure that this x is from the equilibrium position. If you've got a mass on it, make sure that the mass is already hanging at some new equilibrium position. A lot of the conceptual questions will also come with energy, sort of where energy is the most, where energy is the greatest. And these two equations are kind of like that F equals Kx equals ma from the left over there. These are specific conditions. If you are at your amplitude, then all of your energy is potential energy. So you use this equation because your x is your amplitude. And if you're at your equilibrium, you use this equation because 1/2 mv squared is all of your energy as long as your velocity is at its maximum, which occurs at the equilibrium. All of your potential energy that you got from bringing that object out to its farthest point has all been converted to kinetic at that point. Again, here are the equations, and kind of like with the period equations, know what affects each one of these. If you change the mass of a spring that you stretched all the way out, let's say you swapped the masses out and gave it twice the mass, you still are going to start with the exact same potential energy. This potential energy is only of the spring, right? We don't get potential energy from our mass at all. And this kinetic energy is only the mass. We really don't take into account the mass of the spring when we get our kinetic energy, the fact that it's moving. So if you change the mass, it will change the kinetic energy maybe, but it won't change your potential energy. Something to think about there. And be able to solve for total mechanical energy. If I give you numbers, you know how to do that. And the other big piece of this test is going to be graph interpretation. And taking one graph, say we had one like this, and being able to pick out different points here where acceleration, force, potential energy are greatest, least, most upward, most downward. So I'm going to try to go through as many of those as I can sort of get right now. So at the peaks and troughs, we have our maximum acceleration. Acceleration is closely related to force, net force equals ma. So at those peaks and troughs where we're pulled the farthest out, that's where we've got the most force. F equals kx. The bigger x is, the bigger F is. And if F is bigger, then A is bigger as well. And when we're not stretched at all, if our net force is 0, then our acceleration also has to be 0 at these equilibrium points. Velocity is different from that. At our peaks and troughs, we come to a quick stop for a split second. So at those peaks, our velocity is 0, and the same is true at the troughs. But we just said that at the equilibrium position, that's where our kinetic energy is the maximum, which means that our velocity is the maximum here. I can't write. Let me go back here. Here we go. Our velocity is the max there as well. And this velocity on the left, because it is moving downward, this is a greatest negative velocity. And up here where we're moving up, this is a positive velocity, or upward velocity, whatever you want to call it. And here, your positive acceleration is right here. You're moving up. If you pull a spring downward, like we have here, then the acceleration is to accelerate it back to that equilibrium. And your negative acceleration is max at those peaks. It's getting a little crowded, so I'm going to draw another one for our potential and kinetic energy. So let's say we've got x and we've got t, position versus time graph, and we'll get the same shape. So at our peaks and troughs, our potential energy is the greatest, equals max, max, and max. And here, our kinetic energy is the max at those equilibrium points. Here, our potential is 0, and kinetic is 0 at these peaks and troughs. And remember, when you take one of these graphs and go to a potential energy time graph, it's going to be all positive, right? We can't have negative potential energy when it comes to the spring constants. So a potential energy time graph, it's very important to sort of label it to give you a better idea about what is happening physically to that object. So let's say the problem said that it was pulled down. You know, a spring was pulled down, released, and then it started on its oscillation. Here's a potential energy time graph. I'm going to say that this is at the bottom, right? If I pull it down to start with, I'm going to start at the bottom. This next piece, this next peak is the top, and it alternates top, bottom, bottom. And each time we get here where our potential energy is 0, we just set up above that our potential energy is 0 at equilibriums. So all of these lowest points are equilibriums. They're not troughs. They're not lowest points of motion. They're just lowest points of potential energy. And if we sort of wanted a kinetic energy graph to look at, it would just be the inverse. Oh, there we go. Try to fix that a little bit. There we go. It would just be the inverse. The peaks would happen at opposite times, and that is because that this peak here, along the tops of all those peaks, that highest point is our total mechanical energy. And even if we lose energy, let's say we lost some energy to friction, that total mechanical energy sort of line would still hit along those peaks. It still sort of makes that swooping motion and hits those peaks. And one of the things you'll be asked to do with either of these graphs is take information off of the graph and use it in those equations, right? We can get maybe the total mechanical energy off of this graph, and if I give you the amplitude, then you can solve for the spring constant. Or if I, let's say I gave you some information about maybe the spring constant and the amplitude on this graph, you could then find your total mechanical energy, your maximum potential energy. So just keep that in mind, that sometimes you have to pick a particular piece of information off of one of these graphs or multiples of these graphs. And in doing that, make sure that if you're picking a piece off, right, if you know the time of whenever it is. Make sure that all of the pieces you're using in those equations match up with that time. You can't take maybe the potential energy here at time 0 and then the kinetic energy here at 2 seconds later. They've got to match up at the same points. And the last thing that I really want to worry about is making sure that we can go from the position graph to the velocity graph to the acceleration graph. So if we take this here and we say that this is our position versus time graph, and I'm going to draw it like this. And I want to get a velocity time graph. Velocity time. And I'm going to say that this has a period of maybe 8 seconds, which means that that's at 6, 4, 2, and 0. So I'm going to draw out that same graph here. 2, 4, 6, 8. So I'm going to look for places where I know what the velocity is, and that's either going to be a maximum, minimum, or where my velocity is 0. And we said on that last slide that at the peaks and troughs, our velocities are 0. So I'm going to put a point there and a point here. And now I really just have to decide, am I starting from the top or from the bottom? I know I've got to get a sine sort of wave, so really my two options are either this or this. They've got to cut through those two pieces, and those are the only way that's going to happen to get a period of 8 seconds. So I'm going to take a look at this first graph and say, all right, at the time 0, I was on the way up. That means I have to have a positive velocity, which means I have to start with a positive velocity here, and then I make my graph. As you're sketching these graphs, make sure that if you do know what the amplitude should be, sort of what your maximum velocity is or your minimum velocity, make sure that your graph hits there, right? Make sure that this is your minimum and up here is your maximum if you've calculated that. Secondly, make sure that these points hit at the right time. Make sure that your equilibriums hit at the right time. Make sure your peaks and troughs hit at the right time. And lastly, make sure you're starting from the right position, whether it is top or bottom for some other problems. And the same sort of rules apply for your acceleration time graph. So acceleration versus time, I'm going to do the exact same thing. I said that I know that at the equilibrium, my acceleration is going to be 0. So 2, 4, 6, 8. I'll do it in blue. So every time I'm at the equilibrium, my acceleration is 0, 2, 4, and 8. And at the top, I said that I have a great downward acceleration. If I pull something up, if it's displaced upward, its natural, the way the spring wants to take it is back down to that equilibrium. So at the 2-second mark, I have my maximum negative acceleration. And then I just make my little sine wave. Again, the points have to match up. In order to find those accelerations, you might consider kx equals ma. And to find those minimum and maximum velocities, you might consider total mechanical energy is 1/2 mv equilibrium squared. Just, food for thought. The last thing I want to do is just remind, I know I've said it in class, but here as well, the best sort of worksheets, if you're looking for problems to work out, the best ones to do that with, erase that, are going to be worksheets 6 and 7 in the homework packet. I don't think I passed it, did I? Yeah, worksheets 6 and 7, if you recall these ones. There's 6, and 7 as well. Those are going to be your best bets, to be perfectly honest. Yeah. And as well, the unit review questions. These are always good. For many of you, again, some of these are problem-based, sort of calculations, but there's at least a couple. There's a graph one. There's another graph one. There's a third graph one. Graphs might be important on this test. I'll just go ahead and say it. But this number 7 has got some of those concept ones. Which of the following changes result in a change of period of a simple harmonic oscillator? Choose all that apply. Remember, simple harmonic oscillator just means the spring, not necessarily a pendulum. So if we're going to change the period, we said from that equation, T equals 2 pi square root of m over k. So really anything that's going to change the mass or change the spring constant. So A and D for that one. Doubling the amplitude. Amplitude doesn't affect the period of either of them, and moving into a planet with twice the gravitational acceleration would affect our pendulum only. And for the pendulum, mass does not matter, amplitude does not matter. New planet and length are the two things that affect our pendulum. And last, we've got a mass oscillating horizontally. When it reaches the extreme right edge, a second mass is placed on top before it returns. Which of the following in the system, which of the following change for this system? And this is kind of what I was talking about at the very beginning, about how our spring is only potential energy and our mass is only kinetic energy. So if I change the mass, I'm not changing my total mechanical energy at all. Because at that amplitude, when it reaches that extreme right edge, all of my energy is my potential. So if I did not change that because I didn't change my 1/2, my k, or my a squared. I didn't change my amplitude at all. In fact, I didn't change it. My equilibrium velocity is going to change though, right? When I get back with that same amount of total mechanical energy and plug that in for 1/2 mv squared, my velocity, I'm sorry, not my velocity, my mass got bigger, right? I reached and I applied a second mass to it. This mass went up. In order to keep that same total mechanical energy, this velocity has to go down by some. So my equilibrium velocity is going to get lower, and my period's also going to get lower. Again, back to this equation here. If I change my mass, it changes the period. So hopefully this is helpful, gives you a little bit of direction going forward onto the test. I like when people do well because it's less work for me, and I'm lazy. So hopefully this was helpful. And I will see you all tomorrow.